I've been working in the Department of Surgical Research of the University of Szeged. This department's traditional field of research is built upon methane. So, what we know of methane? This is the simplest carbohydrate, and it's considered an inert gas. Traditionally, methanogenesis was bound to the archaea bacteria exclusively. And these bacteria are found in mammalian intestinal flora, so in human guts too. Probably in this room, the majority of people are supposed to be non-methane producers, because in Central Europe, approximately 20% of the population can produce methane. In Japan, it's 15%, which is considered a low amount, and in South Africa, it's really high, it's 84%. All these data are according to the latest publications. So, behind the factors of being a producer or a non-producer are still not clear, but we know some of them. For example, it depends on the lifestyle, the age. Almost all the methane producers are adults, but it doesn't depend on the sex. So, not that long ago, in 2006, a new article came out. A phenomenon of non-microbial methane production was observed in vitro and later on in vivo, for example, in endothelial cells, in higher plants and fungi, and our department had a rat model with chronic alcohol consumption. They all had the same result, which was non-bacterial methane production, and all had the same trigger as well, which was oxidoreductive burst. This oxidoreductive burst might be a cause of mitochondrial dysfunction, which would mean mitochondrial dysfunction causes non-microbial methane production. So, we still don't know the exact mechanism behind this action, but recently a study came out which was about non-microbial methane production from organosulfur components. And all these experiments happened in a vitro. So, it raised the question whether it is possible to identify new biomolecules with methanogenic capacity in mammalian organisms. So far, we've been suspecting this chemical function group for non-bacterial methanogenesis. So our main aim of study is to determine the potential of methanogenic capacity of biomolecules rich in organosulfur components. How did we do our measurements? We used photoacoustic laser analyzer, which measures real-time online methane production. So methane has an absorption spectrum, and absorption creates an expansion. And this expansion creates a sound, what we call the photoacoustic signal. In the first setup, we only used chemicals from our previous research. This experiment was for formatting oxygen-free radicals with catalytically active iron, ascorbate, and hydrogen peroxide. And the next step was adding biological materials. We chose two of these materials, one with high organosulfur-containing biomolecules. This was the mustard. And the other one which is low in these compounds, and this was the coriander. All these reactions happened in a gas-tight cuvette. And what we found was, from the mustard seed extract, significantly more methane generated than from the other two groups. So we applied this knowledge to our in vivo experiments, and we used furless mice for these experiments, which were divided into 3 different groups. The first group was the control group, which was fed with conventional diet for 7 days. The second group was given a 10% mustard seed-enriched diet for 7 days as well. And the third group was given the same diet as the second one, but for 2 weeks. We measured their body weight, whole body methane production, and food mass every second day. And at the end of the research period, we took tissue samples from their liver and kidney for biochemical measurements. And what we found was there was no significant difference between the 3 groups in methane production. However, in their kidney, we saw the tendency of TiO content elevation, but it wasn't a significant change. However, in the liver, it was a significant change in this TiO content. By the way, thiol are organosulfur moieties, and these are the group which are responsible for this unpleasant smell for sulfur-containing biogenic material. In summary, what we found a significant and immediate increase from master seed extract in vitro. And let me highlight the fact that we used healthy animals, and no change in methane production was observed in vivo. Nonetheless, the quantity of organosulfur-containing biomolecules was increased by the given diet in the liver. So it might be an effective tool to influence the methanogenic reaction during pathological conditions. So, based on this knowledge, it would be a logical idea to set up an animal model which is exposed to stress. So we started this experiment with photothrombotic ischemia by means of a photosensitive dye. And we're measuring free radical release and mitochondria function. And we're curious about methane generation and whether the diet group produces more methane than the control group. Another promising approach is exogenous methane application. So another team in our department set up a hypoxic animal model which inhales methane to research the potential benefits of methane inhalation. And we recently started dissolving methane into transplantational fluid to map out the potential benefits for this organ storage. I'm really grateful for this opportunity to work in this department, and I'd like to thank the staff for their help, the supervisors Mihály Boros and Eszter Tuboly, my co-worker Petra Valga for her precious help, and I wish to thank the Photoacoustic Research Group, Árpád Mohácsi and Anna Szabó for their help, and I'd like to thank you for your attention.